While you're finding your seats, I think I'll just gonna start here. So thanks everyone for coming. My name is Seemann, and if you want to know more about me, there's information on blog.plur.dk. This talk is about software development productivity. So I think a lot of us have this experience that development productivity is not as good as it ought to be. And even if we ourselves as programmers are very impressed with ourselves, it often tends to be the case that our stakeholders really aren't. So we're not delivering as fast or as efficiently as a lot of other stakeholders would actually like us to. And if we introspect, I think it's probably we sort of understand that as well. We would like things to work better than they actually do. So this talk is about that. And I'm not saying that I have the silver bullet. I don't have the one solution to that problem. I just have some thoughts about that problem. So I think it's a multifaceted problem. There's more than one reason why software development productivity is not as we'd like it to be. But I think one of the main reasons, one of the fundamental reasons is basically that code is difficult to read. We spend a lot of time reading code. So Robert C. Martin in one of his books says the ratio of time spent reading versus writing is well over 10-1. I'm always a little bit surprised with the numbers that Robert C. Martin comes up with. I think he sort of pulls them out of a hat. But let's just go with that. I don't think he's completely far off here. So let's just use that as an argument. So if we want to try to illustrate this with a figure, we might draw a figure like this one, where we say we have 10 orange boxes here, and that represents the time that we are using to read existing code, and then we have that one green box that represents the time we actually spend writing new code. So that represents a 10-to-1 ratio. And often when we are talking about software development productivity, we tend to have a focus on writing new code. So if a software development vendor, an IDE vendor will tell you about productivity, they'll often try to sell you a new version of their IDE, and they'll demonstrate how you can write code faster. The same thing goes with language design or libraries. Library developers will come and tell you, use my library instead of the other library, and you'll be able to produce code faster. And that's all good. I don't have any problem with that. But let's just, for the sake of argument, make a hypothetical assumption that some revolutionary technology comes by that enables you to write code in half the time as before. So that looks like a 50% reduction in the time you actually spend, writing code. That's probably not realistic. Improvements in productivity in terms of writing code tend to be on a much smaller scale. And it's not that I have anything against those things. I'd like to have the new IDE and the new libraries and so on so that I can feel that I'm more productive. So that's fine. I'll take everything that I can get. I just think that we have to realize that this is not really where productivity gains lie. This completely unrealistic example of reducing development production time, code production time with 50%, that's more like a 4.5% percent reduction in the time you actually spend with the code if you don't do anything about readability. So fine, I'll take the productivity improvements that I can get with writing new code, but if we want to really do something about software development productivity, we probably should do something about readability, because that's where we spend most of our time. So that's sort of like the idea here. So the question is, when is code readable? Now, if you look at code like this, is this readable or not? And you may have all sorts of opinions on whether that's the case or not. So if you're used to reading C# code, you'd probably say that looks readable to me. Not without actually trying to understand it, but just it looks readable. It probably is. But if you are a Java developer, you think it's completely unreadable because I put the curly braces in the wrong places. So yeah. But anyway, so we can't really have these, we can't have these subjective discussions about whether or not something is readable. That's sort of like, I'm standing over here in this corner and say, my code is readable, and then someone comes by and says, no, it's not. And I'll go back here, yes, it is. And then the other guys say, no, it's not. And it's like kindergarten argument level of things here. So that doesn't really work. So we need to have something that's a little bit more, objective. And I'm not going to give you any sort of scientific truth here. I'm just going to give you some tools that will enable you to pull the discussion in the direction of being a little bit more objective about discussing those things. So we probably need to understand what actually happens when we read source code. So researchers who have been looking into that problem, they've defined a couple of terminology for that. So one of the things that they call it when we read code, they call it tracing. Another term for that is called cognitive compilation. So it's almost like we're sort of trying to compile the code in our heads, and we're running a little emulator in order to try to understand what's actually going on. So I'm going to walk you through a little bit of what the brain might do when it looks at code like this. So that means I'm going to spend some time with this particular code example. And the point of spending time with this code example is not to walk you through what the code actually does. It's not really that important. The code is from my notebook, Code That Fits in Your Head. All the code that you're going to see in this session is from that book. And it's the same example or the same scenario all the way through. It's an online restaurant reservation system, but it's not that important really. So what happens in our brains when we're trying to read code like this? Now, we're trying to sort of make sense of it, trying to compile it in our brains, and we also sort of try to run it or interpret it in our brain. And that means just like the actual computer, when it executes code, your brain will need to keep track of state and maintain state. So one of the things we might notice is that there's this object here called allocation, and it's a list of tables. And if you're not a C# developer, you may not know that particular class. But this is a collection of things that you can modify in various different ways. You can add things to it, you can remove things from it, you can reorder it and do things like that. So this is a thing that might potentially change state. So when you're trying to understand what the code does, if you haven't read all the way through already, you say, oh, this might actually change state, and the state might actually impact what the code does. It doesn't, but it might. So that's something that I need to keep track of in my brain. So it's sort of like one thing that I need to keep track of. And then you go on and read some more, and you notice there's a for each loop, and you know that if you're for eaching over something, but that something is empty, you're basically just going to fall all the way through, and nothing's going to happen. You're just going to return the allocation. On the other hand, if there's at least one item, you're going to start looping over those things. And then there's this thing where we are trying to find, in the allocation, we're trying to find a table, it's a restaurant table, we're trying to find a table that fits a reservation request. And that find method will return the table if it finds something, but it might also return null. So this funny thing where it says, if table is curly brackets, that's sort of like a C# pun. It basically means if table is something. It's just a more brief way of saying if table is not null. So table may be null. In that case, we're still going to fall through and we're not going to execute what happens inside of that indented code. But if we find a table, we're going to start mutating and changing the state of that allocation. So in this case, it's fairly easy to keep track of what's going to happen because we remove a table, but then we sort of add it back together with some different states inside of it. So the number of tables at least actually stays the same. So this is fairly straightforward to keep track of. So I'm not trying to tell you that this is hard to read. I think actually this is readable code, not because it's written in a particular way, but because there's not too much stuff going on. You basically have to keep track of one piece of mutable state, and it doesn't really change that much. And these three alternative pathways through the system, some of you probably know this already. This is called, this is a measurement called cyclomatic complexity. And we can see that as a measurement of, how many different alternative pathways do we have in a system. But a method like this one, since it can have three different pathways through the system, it also means that unless we can sort of find some sort of abstraction that captures all that it does, it's almost like it's three alternative universes that are sort of superimposed on top of each other. So unless we can find some sort of common abstraction that describes what's happening here, it's sort of like we have to keep track of or think of this method as being three things in one go. So there's a little bit of stuff to keep track of. In one way of thinking about it, there's one piece of mutable state. In another way to think about it, there's sort of like three different pathways. So how good is our brain at dealing with complexity like that? And it turns out that it's okay, we can deal with that. But there's this paper from 1956 by George Miller called The Magical Number 7 ± 2. That basically says, in our short-term memory, we can keep track of about 7 things, give and take. And it's a fairly robust result from experimental psychology. It's basically been standing for more than 50 years. Other researchers have tried to reproduce that result, and they arrive at, at least the same order of magnitude. Maybe a little bit less, actually. It tends to be, the newer results may actually pull that number down, but I'm just going to stick with 7. So that's really not a lot. Our short-term memory is 1 byte. Okay, and it's a 7-bit byte. Those things actually existed if you go far enough back in time. In the 1960s, there was this thing called a 7-bit byte. So that's not a lot. So what Miller did was that he asked people to remember. One of the exercises he asked his research subjects to do was to remember random numbers, but he also asked them to remember other things. So in general, he talked about those things as being chunks of information. And I'm just going to switch over here and start a little animation. I need to do something because otherwise this is never going to finish. Hang on. I'm going to set that to 120. I'm going to scroll up. Oh, Jesus. All right. There we go. All right. So now we have these chunks, and I'll talk to you in a moment why this animation is now running. But the point is, if you have a completely new code base, and that code base is just hello world, there's basically just one thing that goes on, and that fits in your short-term memory. If you can keep track of about 7 things in your short-term memory, you can understand hello world. But when you start to add more code to a code base, there's just going to be more and more things that you sort of need to keep track of. So very soon there's going to be more than 7 things that's happening in a code base. So real code base will probably have 7,000 things going on, or 7 million things going on, and that doesn't fit into your short-term memory. So what do you do if real code bases have a lot of stuff going on and it doesn't fit in your short-term memory? Now, the computer doesn't care. As Martin Fowler wrote, any fool can write code that a computer can understand. Good programmers write code that humans can understand. So the computer doesn't care that there's 7,000 things going on, or 7 million things going on. It's just going to store those things in memory and access them, all the information as it needs, to make decisions upon those things. And it doesn't really care. The computer will deal with this problem, without problems. We'll deal with that without having any problems with it. So what do we do as programmers when we are faced with this problem that in a real code base there's a lot of stuff that goes on and it doesn't fit in our short-term memory? Now we have this other memory system called long-term memory. It's very creative, short-term and then long-term. Sort of like makes sense. Anyways, so I remember a couple of years ago I had this opportunity to talk to an organization that had a lot of legacy code. So they asked me to come and see if I could help them with that. And I had a chance to interview some of the people who work with that code base. And one of the programmers was the latest addition to the team. He'd been in the team for 2 years, and I asked him, so you still have, and fresh in memory, what it was like to start in this code base that already existed when you were hired. How long would you say it took you before you were able to work on your own in that code base? 3 months. He didn't even think about it. He just said it took 3 months before I was able to work on my own in this code base. So I think what happens in those situations is that we can't use our short-term memory in order to work with code bases like that. So we have to rely on our long-term memory as well, instead. But the long-term memory works in a completely different way. It tends to take a long time to actually commit information to long-term memory, and you sort of have to reinforce what you learned in order for the memory to actually stick, in order to make it accessible to you later on. So he probably, this programmer, he probably spent a lot of time trying to look through the code base and make experimentations with it in order to sort of build up a model of the code in his long-term memory. And after having done that for 3 months, he felt that he had a good enough understanding of that code base that he could actually work with that code base for himself. So it's not that we it's not that we can't write code if code doesn't fit in our short-term memory, it's just very inefficient. This explains why we are spending a lot of time reading existing code, because if we're relying on long-term memory, we sort of have to spend all of that time to sort of commit things to long-term memory. So you'll probably notice that while I've been talking, this animation runs, and at the beginning we just had some chunks of information, but there's sort of we keep on adding more and more of those chunks of information, and they try to self-organize. So you sort of see this hexagonal grid, this honeycomb pattern emerge. So that's sort of like a view of a lot of information that is sort of compacted together as compactly as you can do that. So if we want to do something about the readability problem, maybe we should start to try to leverage our short-term memory more and rely less on our long-term memory, because our short-term memory is quite fast. It's very ephemeral, so you can easily sort of load some information into your short-term memory, but you also know that you can also easily forget those things as well. And that's both a blessing or a curse. But if we could leverage our short-term memory more for programming, that means we can sort of deal with things in a much faster way, because it doesn't take that long time to commit things to short-term memory. You don't really commit it, you just sort of get an idea about how things are, you have it in short-term memory, you work with it a little bit, and then you forget about it again. So even though we have thousands of things going on in a code base, we need to figure out a way to isolate at most 7 of those things and look at, being able to look at that in isolation. So if we take, 7 of those, cells out of this hexagonal grid, we might arrive at a figure that looks like this one. So this is 7 hexagonals, picked out of a regular grid of hexagons. So I call this a hex flower because I think it looks a little bit like a flower, with 6 petals, and then the center of the flower. I don't know what that's called, but it's just sort of like looks a little bit like a stylized flower. And we can think of this figure as a symbol of our short-term memory. And again, I want to remind you that it's not that short-term memory is exactly 7. This is just sort of like a symbol. It's sort of like a logo for short-term memory, if you will. If we want to respect the cognitive constraints of our short-term memory, we should organize code so that whenever we look at a piece of code, there should be at most 7 things going on. And that probably means a lot of abstraction. So at a certain level of abstraction, there should be at most 7 things going on. But we also know that we may have an object that sort of counts as one thing, but then if we want to know how that object actually works, that's when we zoom into one of those things, it turns out that has some complexity in itself. But if we go and look at that code, again, we should have organized the code in such a way that there's the most 7 things going on, because then we can work with our short-term memory instead of working with our long-term memory. So we need this to happen on multiple levels of abstractions in our code base. And you can imagine you keep on zooming into more and more details, if you will. So maybe you arrive at a piece of code like this one. And this is a piece of code that sits on a repository class, and the responsibility of this one is called create. The responsibility of this one is to create a row in a database, a relational database. And the reason why I wanted to start with this one is that it represents sort of like the most granular level of abstraction, in the sense that there's no more user code hiding behind this piece of code. We have some objects that are being instantiated here, but the objects, SQL connection, SQL command, those are framework code. These come from the .NET framework. They're not our own code. So unless we want to go and read the source code for the .NET framework, there's really nothing more we can do from here. We can't zoom in and go and look at the definition of how does SQL command actually work, because we don't have easy access to that source code. So that's sort of like the lowest level of abstraction. So we can ask ourselves, the question, is this code readable? And again, instead of having the kindergarten argument where you're relying entirely on subjectivity, we can try to use some quantification or some measures to quantify these things and say, if there's more than 7 things going on, it probably doesn't fit in our short-term memory, so that makes it less readable. So one of the types of analysis we can try to do is what I just talked about before, cyclomatic complexity. We can sort of try to measure how many different pathways do we have through this particular method. And there's only two, because either reservation is null and we throw an exception straight away, or we run through the rest of the code. So that's pretty good. If we're thinking about cyclomatic complexity as this thing where we represent two alternate realities that are superimposed on top of each other, that's two things that we sort of have to keep track of at the same time in our brain. But if we can keep track of 7, that's fine. That's well within capacity. So according to that measurement, this code should fit in our head. Now, we can also try to figure out if there's state that we need to keep track of. So just as a coarse measurement, unsophisticated way of measuring this thing, we can just try to count every object that's actually being involved here. So we have a restaurant ID, that's one method argument. We have this thing called reservation, that's 2. We have something called the connection string. You can't really see where that comes from, but that's a read-only property. And if there are people here who are not C# developers, a property is just a glorified class field, basically. So this is a read-only class field. It's a string. It just contains the information about how do we connect to the database. So we use that to create a connection object. I'm just going to keep on counting here. I use that connection object together with something called create reservation SQL. That's another string. It's not a class field. It's just a constant string that just contains all the actual T-SQL code that will be executed against the SQL server. And then we use those, that one and the connection to create a command object. So that's 6 things, and then there's actually no more things being created here. So that's 6 things. So if all of those things were mutable objects that would potentially change state, we might still be able to follow along here because we can keep track of about 7 things, and there's 6 things going on here. So yeah, we're probably good. 7 plus minus 2, maybe 6 is a little bit too much, but we're probably good. And I think we're better off than that, because it turns out that the things that actually do change state is con and command. You'll notice command changes state 6 times just after it's been created, because we add parameters to it. And then towards the end, we change the state of the connection because we open the connection to the database, and then we execute a query against it. But all the other things actually don't change state. And there's a natural explanation for that, because if you're thinking about the first one, restaurant ID, for example, you say, oh, but that's an int. And ints are immutable. They're not going to change state. And that means it's not going to tax our memory quite as much, because it's not really, I'm not saying that the value is not important. This integer, I'm not branching on this particular integer, but I might branch on an integer. I might say, I might have some other code that says, well, if the integer is less than 0, I'm going to do one thing, and if it's more than 0, I'm going to do something else. But at least it's not going to change state, even in a case like that. So things that don't change state are a little bit easier on our memory. We can think, we don't have to sort of think about them that much. So that also goes for strings. So the 2 values labeled 3 and 5, those are strings. They are immutable as well, so they're not going to change. So it means that basically, con and command and maybe reservation are going to change. Now it turns out that I've written reservation in the way that it's an immutable class. And I've done it for various different reasons, but one of the reasons is exactly this. Immutable things are just easier on the brain because they're not going to change state. So I basically designed most of my domain code in this code base as it being immutable classes, because that's just easier to think about, less taxing on the brain. So this is also what in domain-driven design is called a value object. Not a value type, but a value object. So we can be more sophisticated with this kind of analysis, but even if we're just being unsophisticated and just count all the variables, it's sort of like, yeah, we are within the capacity of 6. We can try to enumerate them, or just for the sake of illustration, we can try to associate each of those things that we have to keep track of in our brain with one of those cells in our short-term memory. So again, I remind you, this hex flower is just sort of like the logo for our short-term memory. So that's sort of like the idea that as long as you can sort of fit things inside that structure, it fits your short-term memory. Right, okay, so you might say, okay, so we started by, the first example that I showed you here, the create method, that's the lowest level of abstraction. This is where there's no more user code hidden behind behind that method because you're just calling into framework code. You're calling into SQL connection and SQL command. But we're probably going to have some other user code. In my code base, I'm going to have code that calls that create method. So you might say, well, but there's 6 things going on inside of that create method. So if I need to think about those 6 things, and then on the next level of abstraction, when I'm looking at code that calls that, if those numbers compound, that's not going to work because then I'm going to exceed my threshold of 7 very quickly. So it's really important to make sure that when we're looking at things from the next level up, whatever complexity there's in an object or in a method, that should collapse into just being one thing, one chunk of information, because otherwise our brains cannot keep track of it. So if we want to be able to zoom out and say, okay, on other levels of abstraction, whatever was inside of each of those things is just going to collapse, and we should be able to think about that as being one chunk, because if we can't fit the code in our short-term memory, and then we have to rely on long-term memory, which is much more inefficient. All right, so this applies all the way to the entry point of the application. So the entry point of the application looks like this. This should also fit in your head. And I don't want to turn this into an ASP.NET tutorial, but that's the code that I used. So this was basically created by a wizard. I didn't write this code. It's just the Visual Studio said, okay, I'm going to create a new ASP.NET application. Okay, here's your entry point. So if you've ever seen things like that, all the interesting stuff happens inside a class called startup. But at least we can still try to count things and say, okay, so what's the cyclomatic complexity here? It's just 1. There's really no branching going on. How many things are involved? It's just those 2 things are involved. So that's fine. I don't have any problem with that. So I can move on and look at the startup class, which is where all the interesting things are happening. But the point is, whenever we want to look at another level of detail, all the surrounding stuff that exists at one level of abstraction should now go out of scope. So if I want to look at startup, I need to be able to understand startup without understanding that there's a thing called arcs or there's a thing called web builder. And fortunately, that turns out to be the case. So here we just have the public API of the startup class. And if you've ever seen one of those things before, you'll note that by convention, it has these 2 configure methods. And again, this is not an ASP.NET tutorial, so it's not really that important. There's also a constructor that takes a configuration object as input, and that configuration object is then later on available as a property or glorified class field. So I sort of count those as one thing. So basically, at that level of abstraction, there's not a lot of stuff going on. So it fits in our brain. It's easy. It's easy enough to sort of just look at that with our short-term memory, even if you haven't seen this before. That's the entire point. You can say, okay, I understand it at that level of abstraction. There's not a lot of there's no detail here, but at least I'm not confused at this level. So now you can say, well, I want to look at what happens inside some of those things. And if you've seen ASP.NET code before, you know that most of the interesting things happen in configure services. And again, if you go and look at configure services, you should be able to look at configure services without understanding what's happening over in configure, because if you also have to understand what happens in configure, that's going to overload your brain. So each of these things sort of have to have, a scope where your brain can work inside of that scope and understand what's going on. So if we look at this code again, we can try to ask ourselves the question, is this readable? And again, I don't want to rely on subjective judgment, so I can say, let's try to quantify it. And again, I want to reiterate that these sorts of quantifications, like looking at cyclomatic complexity or just counting the objects that are activated, it's not a rigid measurement. It's not something where you should sort of set a target goal as such, but it gives you an opportunity to have a discussion about when things become too complex. So if we're trying to ask the question or answer the question of is this readable or not, we can say, what's the cyclomatic complexity here? Because that might be one dimension we might want to consider. And it turns out that it's 1. There's just a straight line through this code. There's no branching, there's no looping going on. So it's pretty straightforward. What about object activation? How many objects are involved here? And it turns out that there are 6 objects involved. Now, most of these ones are actually mutable objects, so they're a little bit more taxing on our brain if we want to actually go through and look at that, because these things can change state, and they do. So this is probably more on the edge of what's actually, fitting in our short-term memory than the other example that I showed you. But I don't want to go into a detailed analysis of this, so let's just leave it at that. So you'll notice that I have a little bit of, the code continues below the screen here, but there's really nothing. It's not a trick. I didn't hide anything important from you. But the point is, again, at this level of abstraction, the code fits in our short-term memory. And it's not that you're getting all the answers to all the questions that you might have if you're trying to understand what's going on in this code base. You're still getting some high-level information, and maybe you are at least getting enough information that it's sort of easy to figure out what to do next. So if you want to know something about, for example, what's the security model of this system? Do I require, some sort of log on? Maybe you can see, they have this thing called configure authorization. Maybe I should go and have a look there if that's what I'm interested in. And if I go and look at that method, again, it should be organized in the same way. So it should be organized so that at most 7 things are going on. And again, if I go and navigate to that method in order to understand the code there, I shouldn't have to remember what happened at this level of abstraction. So all the stuff that we're looking at the moment should now become irrelevant in order for me to understand what happens inside of configure authorization. And the same thing goes, if you're more interested in looking at what happens with the persistent storage in this system, you might say, repository, that sounds promising. Maybe I can learn about the storage system if I go and look at that. And again, if you navigate to that method, you should be able to learn something about, how the storage system is working, how SQL Server is configured. But what happened inside of configure authorization, or what's later going to happen inside of configure restaurant or configure clock, should not be important in order to understand what happens inside of configure repository. So each level of abstraction should come with its own scope of understanding, and you have to be quite deliberate about designing what's in scope and what's outside of scope. One of the things that really kills our understanding of things is if we have global variables, and I think most of us know that global variables are really evil. But the problem with global variables is that they're not visible, they're not in scope, but they might still affect how the code actually executes. And again, the computer doesn't care. There was this famous incident, a famous problem with Toyota. They had this thing called the unintended acceleration bug, I think they call it. They probably didn't call it a bug. But there was this thing that actually killed people because sometimes the Toyota computer would decide to accelerate instead of brake. And they had a consultant look through the code, and he counted, he said they had about 10,000 global variables in their code. And again, the computer doesn't care. It's just going to say, okay, I'll put all those 10,000 global variables in RAM, and I can access RAM, as I'd like to do. By the way, have you ever wondered about why is it called random access memory? It ought to be called arbitrary, access memory, AAM. It's not random, it's very deterministic. I want that address. You're not saying, give me some random data from your memory. Okay. Anyways, okay, that's completely besides the point. But anyways, so the point is, so this is a little bit of an ad hoc enumeration, but basically organize code so that there's not too much stuff going on. And it's going to be easier to work with your short-term memory. You go and look at the code and you say, yeah, okay, I think I get it. At this level of abstraction, I sort of understand what's going on. And then you sort of find the place where you need to work with the code, and you work with the code, and you sort of work with your short-term memory and say, yeah, I get it, I sort of understand what's going on. And then once you're done working with the code, you commit the changes, and maybe you push them to a pull request or push them to master, whatever it is, and you walk away from the code and you completely forget about it, because short-term memory, as soon as you're not working with the stuff anymore, you've forgotten it. But it's not a problem, because if you want to come back to it, it takes you not a lot of time to actually sort of come back into what's going on there. It doesn't require a lot of painstaking, okay, you can't disturb me for the next 3 hours because I need to work with this code. It's basically just, yeah, I'm just going to use a couple of minutes to sort of look this through and say, yeah, okay, I sort of get it. There's still going to be a lot of searching, finding the right place and so on, but it's just more that you don't have to rely so much on your long-term memory. So One thing that I promised to get back to is the question of, if we are looking at things from a higher level of abstraction, how do we know that we are that we're not leaking details? Let's see if I want to look at this one. Actually, I want to go back, and I can't go back because of all my animations. So I'm going to do this, and then I'm going to restart it again. No, not that. This also advances, automatically. Let's see. Okay, we'll go here. Okay, right now. Okay, so so what I wanted to do here was to talk about, okay, how do we ensure that all the complexity that might be contained at a certain level of abstraction, that complexity doesn't escape to the next level, because if you have stuff going on at one level of abstraction, at the next level of abstraction, you want that thing to be just one thing. This is basically, what Bertrand Meyer talked about when he talked about object-oriented design back in the 1980s. He was the guy who invented this language called Eiffel, wrote a quite important book about object-oriented design called Object-Oriented Software Construction. And he talked about this, the idea of an object is basically to have something that he calls an abstract data type. So it's sort of like it's a data type that it contains data, but you don't really know how it's implemented. You just know how to interact with the object. So you can think of an object of arbitrary complexity as being just one thing. And in the science of experimental psychology, that one thing, instead of calling it an object, we call it a chunk. So that's sort of the thing we want to be able to do. We want to be able to look at a module or a thing, a collection of code from the outside and think of it as being one thing. That is the point of encapsulation. So in general, encapsulation turns out to be a really important thing. And there's there are multiple books about how to write code with good encapsulation. Well, you can read this one, for example. But there's an easier shortcut that you can sometimes use, or actually quite often use, and I want to talk specifically about that one. So in general, there's a lot of art and a lot of learned knowledge about how do you write code with good encapsulation, and there are lots of rules of thumb. But if you can do it in a specific way, it actually becomes fairly easy. So that's why I wanted to talk about this allocate method that I accidentally zoomed in on a little bit too early. So this is the allocate method that you've looked at already. And this one has a little bit of complexity, because I already talked about this sort of this cyclomatic complexity of 3. And if we allow that complexity to escape, if it leaks out into the next layer of abstraction, if I have to think about those 3 pathways through that code whenever I'm thinking about the allocate method as looking at from the outside, then I've used almost half my budget if my budget is 7, so that's not going to work. Also, if we are trying to be just coarse-grained and count all the variables that are involved here, there's actually 6 things going on here. So you might wonder why it's always 6. And the reason for that is I tried to take my own medicine when I wrote this all the code for the book. So I would actually go and look at those measurements, and whenever I would reach 7, I would say, okay, that's becoming a little bit too much, so I'm going to refactor the code. But I left a lot of things in the code where the number was still 6, because I thought, okay, that's just one below the limit. I can get by. I can live with that. So you'll find that throughout the code base. So anyways, also, that kind of complexity cannot be allowed. We can't allow that to escape to the outside, to the caller of the allocate method, because then we've used the entire budget of our short-term memory. So we can't require that the caller understands all of this stuff. This has to collapse to just being one chunk. And I would claim that is also the case. This allocate method does not leak implementation details, and there's a very specific reason for that. Now, first of all, this particular code has no side effects. Okay, so side effects are things that change the observable state of the system. So that might be sending an email, and you can look at this and you can say, does it look like it's sending email? It doesn't really look like that. It might be writing to a file on disk, and you can look at this and say, does it look like it's writing to files on disk? No, it doesn't really look like that. And you can sort of think through various different things that might mutate state, and you can say it doesn't really look like it's mutating state. it actually is. It's mutating the allocation, but that mutation never escapes the scope. As seen from the outside, it doesn't change observable state. So there's no side effects. That's interesting. It turns out that this allocate method also has another good quality, and it is that the same input will always return the same output. So again, let's have a look at this. If the reservations is always contains the same values, and we also have this thing called tables, which is a read-only property, like a glorified class field. If that always contains the same data, then this method will always run through the same sequence of things and return the same output. It's deterministic. So those two things together, deterministic behavior and no side effect, it has a name. This is called a pure function. And the nice thing about pure functions in this context is that they're what we call referentially transparent. And it's one of those things, again, where let's come up with a good name that sounds really scary so that people don't understand what we are talking about. And really what it means is that when things are referentially transparent, it means that the function call and the result that it produces are equal to each other. You don't actually need to run the execution in order to get the result. If you already know what the result is, you don't have to call the method. So sometimes, for example, to illustrate this point, what you could do is you could say, if you have a calculation that takes a long time to run, for example, you might say, okay, so if I made the calculation once, I could create a little dictionary where I key the dictionary by the input, and then I can just save the output in the dictionary. And so next time someone comes by, we can just look it up in the dictionary. We don't have to actually call the function. This is a technique called memoization. It's pretty much like caching, it's just with the difference that things never become stale, because once you know the output one time, you always know the output. So this is interesting because it means that all the stuff that's happening inside of allocate, okay, it's not a lot, but still there's a little bit of stuff going on, it's equal to the output. The output is an enumerable of table. That's basically just a collection of tables. And a collection of tables or an allocation, that's actually what we're returning here, that sounds like one thing. We can think of that as one thing, and we don't really care exactly about how we arrived at that allocation of tables. We just now, on the next level out, we just need to know that here is a thing that represents an allocation of tables. So because it's referentially transparent, this code is equal to whatever it is that it outputs, and that means it just collapses into being equal to its output. It's one thing. And how it arrives at that decision does not leak out into the next level of abstraction. So referential transparency is a really important way of making sure that things don't leak. There are other ways you can do it. There's other ways to think about encapsulation, but I find this one to be the easiest one because there's actually fairly rigid rules for what constitutes a pure function. So that's at least a nice way of doing that. So to reiterate, we need to be able to look at code at various different levels of abstractions. We need to be able to zoom in. We need to be able to zoom out of the code, and we always need to respect our, the constraint of our short-term memory. That's going to make our code much easier to work with. So at the entry point of the application, it might look like this, and we want to be able to zoom in on things and also go and say, okay, what's happening inside of each of those levels of abstraction. So if we think about an arbitrary level of abstraction, you can say, well, there's at most 7 things going on, but we also do understand that even though we don't have to think about it, and each of those cells might, have another 7 things going on, and then, now we have 49 things, and we can't, keep track of that in our head, but we understand that that's the reality of things. And then we also understand that each of those 49 things, if we organize our code in this way, each of those 49 things may contain, another 7 things, and these might contain another 7 things, and so on. That's funny that it looks like this. Okay, so this is really looking funny. Let's see. Anyways, okay. So I don't know why it's doing that. Let's give it one more shot. Yeah, I've never seen it do this before, but basically the idea is that you should have this more lace-like pattern here. Maybe we can look at it later on. But this is a fractal. That's basically the point I was trying to make. And if you were hoping to see Mandelbrot sets or something like that, say that's not a fractal. Well, it would be a fractal if it would actually render correctly. I don't know why it does that. But there's another famous fractal called a cock snowflake. And this basically just goes, you start with something very simple, and then you just keep on subdividing straight lines into those triangles, and you get this snowflake thing here. And this is a well-known mathematical fractal. This is definitely considered to be a fractal. You can keep on zooming in on the edge, and you can keep on subdividing things, in infinity. And the same thing goes with that. Okay, that looks not much nicer. That's actually what I was hoping the other one was going to look like, and I don't know why it didn't do that. So you have to stop, in reality, you have to stop, iterating after a number of iterations, because otherwise it's just going to be, you can't really see the detail anymore. So this one is 4 levels deep, because if I add a 5th layer, it just becomes one green blob, basically, because it becomes so fine-grained. But that's a fractal hex flower, and that's why I call this idea fractal architecture. Let's see, I have a little bit of time, but that's basically the idea. So this hex flower, we can just think about that as sort of like the logo for short-term memory, and we do understand in reality it may not be exactly 7, it might be 5, or newer research says that maybe it's even as low as 2. That sounds almost impractical, but that's sort of like the idea. But anyways, the point is to try to shift our thinking about code and being very deliberate about how we organize code so that we can leverage short-term memory much better instead of long-term memory, because short-term memory is much faster and it doesn't require as much energy. It actually uses less energy, fewer calories. So that's sort of the idea behind code that fits in your head, which is my new book. And I brought a couple of copies here because I'm basically done with the talk. I am done with the talk. I have some time, so if you have questions, I'll be happy to take questions. And the first 2 people who ask a good question, I will have a copy of that. So if you ask me, Mark, what's your favorite color? That doesn't count as a good question. So let's see. Do we have any questions? You had a question already?
What is a good question?
What is a good question? That becomes, so you are asking about recursion. What's recursion? C recursion. Okay. Yes, in the back there. Yeah?
Do you think it's actually a good metric to count variables in your code, or is that just like an explanatory?
Do I think it's a good practice to actually count variables in my code, or is it more for illustrative purposes? Does that capture the essence of your question? Yes. It's not something that I do deliberately all the time. The reason why I started doing that was because people would ask me more about API design. They would say, how many arguments can you add to a method before it becomes too many arguments? And I started to think about that, and for a long time I would just say 4, because that sort of felt like I can sort of live with 4 arguments to a method, but sort of like if you try to add a 5th one, I get this icky feeling. And then but then I started to think about, okay, so why is it that I can often live with 4, but then I don't really like 5? And then I started to think about this sort of thing, where I thought, well, really it depends on how much stuff that's actually going on inside the method, because the more arguments that I pass through a method, as method arguments, the more it's going to tax my brain in order to try to understand all the things that these 4 parameters are going to represent. So you could say if you have nothing else than just inputs, 7 would actually be a good maximum number, because if you don't create any intermediate values or anything else, that's probably still going to fit in your short-term memory. But that's why I started to think about these things. It's because people would keep asking me that question, how many input arguments are too many? So that's how I arrived at this technique. So sometimes I use it when I discuss with other people, where particularly if I feel that they want to add another input parameter to a method, and I say, all right, okay, there's actually a lot of stuff going on here. Let's just try to count how much stuff is actually going on. That's probably going to tax our short-term memory. So it's an argument that I use mostly in a context like that. So it's not that I actually do it every time I'm writing code. So I hope that answers your question. Let's see, can you pass the book down here to the young lady? All right, and I don't want to favorize people who are all in the front here. So this gentleman up here.
In terms of actually applying this method, is there a recommended way to do it in regards of the project structure? Should the code reader starts with utils first and then type into the source code, and would it be in a top-bottom or bottom-up approach?
So you're asking, if I get you right, you're asking whether there's any sort of recommended structure. So are you thinking about, like file structure, for example?
Whether it's files or whether if we're talking about a microservice way of organizing.
Okay, so whether we're talking about file structure or microservices or things like that. So you're basically asking about whether there's an architecture that goes with this. Is that the right way of interpreting your question?
It's about how to apply actually the reading method of understanding this repo or this project.
Oh, so how do you actually, if you haven't seen the source code before, how do you navigate it? That's the question. Oh, okay, fair enough. So I think what I tried to do, and that was probably a little bit of an implicit way of demonstrating that, but the reason why I walked you through, starting at the entry point, is that's, if you've never seen the code base before, and if you don't have a particular goal in mind, you'd probably start by looking at the entry point of the application, because where else would you actually want to start? And then you could sort of try to navigate. So what I tried to illustrate with the walking through the code is that you start at a very high level of abstraction, and then there are probably things that sort of catch your fancy, and then you can navigate to those and you try to understand those, because that might be what you're most interested in. So this is if you're not having a goal in terms of reading through the source code. So definitely, we should enable that sort of reading, and that's what I've tried to do here by keeping all the very high level stuff, still very abstract, so it almost reads like a table of contents. But we should also remember there are other ways, there are other entryways into a code base you haven't seen before. Maybe you start as a new developer on a team, and one of the first assignments you get is that you have to fix a bug, and this bug comes with a stack trace. So if you get a stack trace, maybe you can jump directly into the place where there's an exception, and then you can sort of look at the code at that level. But that code should also be organized so that it respects the limitations of your short-term memory. So even if you haven't started with the entry point, but just basically gets thrown into the middle of it, it should still be encapsulated and shielded from the rest of the world, that you can hopefully get an understanding of what happens inside that small piece of code. And by the way, my experience is that if you're writing pure functions, I've done a lot of functional programming over the last couple of decades. If you're writing pure functions, that is actually not unrealistic. If you're getting a stack trace and you're saying this is where the problem is, and you can see that's a pure function, you can basically start to reason about, okay, some of the inputs into this function must have caused this problem to arise, and you don't really need to understand a lot of the surrounding stuff. So I hope that answers your question. All right. Congratulations with the book. Let's see if I can do this without doing feedback. Oh, really good sound system here. All right. So I'm out of books to give away, and I think I have a couple of minutes left still. So we'll still do more questions. So yes.
Would you apply the same rule of thumb to the abstraction level of an application?
So would I apply the same rule of thumb to the abstraction level of an application? So what do you mean by the abstraction level? I mean, if we're looking at the architecture.
About like the depths you have in these fractals.
Mm-hmm.
And in some code bases, I think it can become like abstraction hell with too many abstractions, so you like lose yourself in too much abstraction.
Okay, right. Okay, so if I may paraphrase what you said to keep people in the back also enabled to follow the discussion. So you're saying, what if you have abstraction, a layer of abstraction on top of a layer of abstraction on top of a layer of abstraction? You sort of get this, you use the term abstraction hill, which I actually think is, I'm going to adopt that now. I really like that. I'm going to pretend that I made it up myself. No, I'm not going to do that. Yeah, so that might put you in a position where you feel that you are it's difficult to actually understand what's going on. That's sort of like your question, isn't it?
Yeah. Would you apply the same rule of thumb with, like?
I would definitely apply the same rule of thumb, but I think abstraction is a little bit of a misunderstood concept because many people tend to equate the idea of abstraction to interfaces or maybe abstract base classes. And you can definitely have interface, let's just stick with interfaces. You can definitely have interfaces that someone meant that interface to be an abstraction, but it turns out that it's not really helping you. Robert C. Martin has this great definition of abstraction. He says an abstraction is something that amplifies the essentials and eliminates all the irrelevant stuff. And if you're using an interface in most languages, there's no guarantee that you're actually doing that. I've seen plenty of examples where the opposite, actually happens. You're hiding away something essential and you're amplifying something irrelevant. So if that happens, it's really messing with your ability to fit things in your short-term memory. So the question is, I understand why you're asking the question, but I think the answer is that the answer lies in having good abstractions. Designing abstractions so that they're actually proper abstraction is really important. And that's not easy to do, but starting by thinking about this thing, does it amplify something essential? Does it hide all the irrelevant things? That's basically also the goal of encapsulation anyway. So that's sort of like that's a good start of it anyway. But I think if you're looking at an interface, if you feel that in order to understand what the interface does, you have to navigate to the implementation that is being implemented by that interface, that's a pretty good sign that encapsulation is actually broken, and that's where you arrive in this sort of abstraction hill, or interface hill. And I think the question here is to come up with, not come up with, but be very deliberate about designing abstractions that are better, because otherwise you're going to run into this problem. All right, I think I can do one. I hope that was sufficient. I think I can do one more, and then we are out of time. Yes, sir.
Well, I was just wondering about the cyclomatic complexity, because you barely named it. And could you first explain it shortly, and then give your advice about what would be the limit for a function?
Right, okay, so you're asking about cyclomatic complexity and whether I could just repeat very briefly what it is, sort of give an intuitive description of what it is, and then what do I think is a good limit, okay? So first of all, I think it's worth noting that this idea of cyclomatic complexity is again one of those concepts that has a horrible name, because cyclomatic complexity sounds really scientific and difficult to understand, but it's really just the number of alternative pathways you can take through a code base. So I think that, it helps to just think about it as that instead. And what should the limit be? And in traditional literature, if you will often see recommendations like 20 or 40 is still considered to be a good a good factored solution. I've actually tried to stick with the limit of 7, and again 7 is sort of like arbitrary because I'm just writing this magical number 7. So if you don't like the number 7, but if you maybe want to pick a number like 10, I think that's probably going to be pretty decent as well. My experience anyway is that you can absolutely write complex code that has a lot of sophisticated features and still design it such a way that you do not exceed the cyclomatic complexity of 7. That's what I've tried to do with the code base. That's what I generally tend to do. I can typically stay well within that and stick with 3 or 4. But it really depends on your level of abstraction as well, because for example, if you're doing a lot of looping, actually for each looping that counts as a branch. But on the other hand, if you then go and use a technique like from functional programming where you do projections, selects and filters and stuff like that, that does not count as branching. So, there's things you can do to keep cyclomatic complexity down, and that's what I typically tend to do. But I think the point is to have thresholds that are quite aggressive, because if you have aggressive thresholds, like for example 7 or let's say 10, what happens is that if you actually stick with those thresholds, the code will never become super complicated. And that means maybe you're staying a little bit to the safe side, but it's better to be safe than to be sorry, right? So I have good experience with sticking below 7 or 10, that sort of order of magnitude. So I hope that answers your question. So I'm out of time, so and I have to rush to room 2 to give another talk, so I'm basically just going to pack down and go over to the next one. So if you want to see that, you can come, but otherwise you can go and see some of the other fantastic talks that are here at the conference. But thanks for coming.